how I learned to stop worrying and love autodiff. And then, I realized I left a crucial part out of that title. And so I amended the title to be Dr. Jax, or How I Learned to Stop Worrying and Love Autodiff. And actually, so I got ChatGPT to create this. I tried for way too much time to get it to make it from a prompt, until I finally just took the screen grab from the movie and pasted it in and said, like, replace the bomb with a computer. And this was the best that it could do. And so for the younger folks who have no idea what we're talking about, there's a movie called Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. It's like a really, it's a classic film that's really funny. It has this iconic scene. But anyways, and so there's a scene where this pilot rides a bomb out of the plane, but here we go. He's riding a computer, okay? So there we go. ChatGPT is useful. But what I thought I'd do today is just gives kind of a high-level overview of what this thing JAX is, what autodiff is, and how it can be useful. And so today, the code that we'll be going over really will be, fairly high level. We'll get to a point where we'll start doing Poisson regression. But the point of this is really just to introduce, what is JAX and what it can be useful for when it comes to implementing our own software, if we use Python. Okay, so let's hop right into it. That's the only slide I have, really. But really, what I thought we could do is just kind of hop around a couple different things. But JAX is this framework in Python that's the marriage of three ideas. The first thing is this notion of just-in-time compilation. And so what that is, it's a concept from computer science and compilers where for programming languages that aren't compiled beforehand, right? So things like R or Python, right? Or Java or C#, right? Those languages are interpreted through like a runtime environment, right? There's a Python runtime environment. There's an R runtime environment. There's a C# runtime environment. It's different from when we write code in like C or C++, where the compiler would take the high-level language that we're working in and write out a binary that's essentially machine code, right? That's like directly something understandable by the architecture that we're running on. Right. And so the reason for what just-in-time compilation is that for languages that are interpreted or like maybe pseudo-interpreted, right, with like some kind of intermediate bytecode, right? What it can do is over the first time a function is looked at, is inspected, right? Like here a function not mathematical, just some code, right? What it can do is traverse the graph that defines that subprogram and spit out maybe C code or C++ code or some code on the back end that gets compiled to the architecture that we're actually on, right? And so what it enables for is maybe just an initial penalty in terms of that compilation that happens at runtime, right? With the added benefit of that we get code that performance-wise, right, should be similar to what we would get for C++ or whatever, right, for free, right? So we don't have to write any C++. And so just-in-time compilation on its own is not new, right? Java's had that for decades. C# has had that for decades. A lot of languages have that, but it's something that Python hadn't had until recently. And so this is a core aspect that JAX brings with it to write very fast Python code, right? Fast Python numerics. And so that's the first thing, and that's kind of maybe a technical, uninteresting but very useful aspect of what JAX is capable of. The second part, and probably one of the more interesting aspects of what JAX is the A, and which stands for autograd. Okay, and so autograd is a Python library that has existed for a while, where the purpose of it is to automatically compute the derivative or the gradient or any generalized notion of that for computer code, right? And it does so not in a way that is like a numerical method of finite differences, right? It's an exact computation of it, right? But we don't have to specify the gradient, right? We just write our code and it does it for us, right? And so we'll see what that looks like in a minute if this is all kind of, way too high level. And then lastly, the X and JAX stands for XLA. And so XLA is this intermediate code, byte code, that's now been sort of opened up and standardized that a lot of these machine learning compiler languages are trying to target. And the reason for this is that, like, why would they want, one might ask, like, why do we need another bytecode? Why do we need new compilers? Compilers have existed for decades. There's like millions of man hours that go into the development of compilers. Like, why yet another one? And I think the primary reason is that while like certainly there's a lot of maybe very complex optimizations that are missed, right? That like might not be yet implemented in something like JAX or equivalent, but there's a lot of optimization specific to linear algebra, right? That might not exist in like your standard, let's say G++ or Clang, right? That's hard coded or like kind of baked in to this runtime, right? And so these three things together kind of are what really define JAX. And it's something that I use quite a bit in my group. And I request, oh, I'm not sharing my screen. Oh my gosh, sorry. Oh wait, am I?
Yeah, you are. We can see
It's
it.
the whole screen. I forgot. I'm not sharing the window. Okay. Should I make this bigger? Is this too small for folks to?
A bit bigger would be great.
Yeah, there we go. How about that? Sorry about that.
Perfect.
Okay, cool. All right, and so that's kind of the gist of what JAX is, and so we'll get into the specifics in a moment. The other thing that I've been using recently, even in one of our classes, is Google Colab. And so here I started this Colab. I can share the link for this later after the talk, or maybe what I can do is just reply to the email. Actually, I can do that now. Copy link. Only people with access, just anyone. That's fine with me. Okay, and then I'll just reply to the Dave's email. Or you know what? The chat. What am I thinking? We can just use the chat, right? Okay, so that way folks can follow along and not just watch me code. But Google Colab is basically like an interactive notebook through the browser. Okay, and it'll be running on their instances, their hardware. So I think by default we get CPU hardware, but if we have some, there's things like we can change the runtime type, we can change the type of machine that we're on. It might cost money to go beyond what's like just the standard thing, but if you really want to, you can have this run on GPUs. Or you can have this run on Google proprietary hardware, what's called a TPU or a tensor processing unit. And that's where it's like their own custom designed hardware made for XLA. I haven't tried that out, but I'd be curious to how that works. And one reason for that, why it's like helpful, at least like kind of get some scratch going on Google Colab with these different things, is that JAX also, earlier I mentioned just-in-time compilation targets an architecture, right? It targets the architecture you're on. But with the flip of a single flag or a single line, right, we can say that we want our JAX code to run on a GPU, or we want our JAX code to run on a TPU, or we want our JAX code to run on multiple CPUs, where it's very high level. It's just one line in our code we have to change. There's nothing special about our code downstream that we need to consider to target any of those architectures. And so having that flexibility where you can just write your software to do its inference and then let the user decide whether or not they want to run on GPU, CPU, or TPU, it just comes for free, right? And so now there's the added benefit of scalability in that we wrote our software just as we normally would without worrying ourselves about having to learn low-level, CUDA or, all these things of how to push stuff to the GPU. It handles everything for us. Okay, so why don't we get started? I'm just kind of blathering here. But the first thing that we need to do is that Google Colab comes with JAX and everything pre-installed, but there's a couple additional things that I'd like to include just for today's lecture. And so in order to kind of execute just sort of command level, sorry, like bash level commands, we need to add an exclamation point in the front. Because what you can think of as these code blocks typically the default is to consider them as a Python code block. And so if we want Colab to know that we're essentially running like a command line operation here, we need to put the exclamation point. And so pip is this Python package manager. Okay, and so we're saying we're letting pip know we want to install this module or package called Liniax. We also want to install something called stats models. I don't know if we'll have time to really use this, but let's cross our fingers and maybe we'll be able to. So let's install these two things. And so, while these are installing, you should see these stuff running below. I'll just briefly mention what Liniax is, but Liniax is a library that's come out in the past year that it focuses on really just two aspects. The first aspect is representing linear some matrices and as a very general notion of a linear operator, right? And what that means is that you can abstract away what a matrix is in some sense. So we can think of the matrix as like the result of some evaluation of a function, right? Or maybe the higher order gradient of a function. Or maybe it's the product of two matrices to generate a new matrix. And so there's this notion of a linear operator, and it has kind of a grammar for how to talk about linear operators. And that might be useful for certain optimization tasks when we want to let's say rather than explicitly constructing maybe like a Hessian matrix, we might only want to deal with Hessian vector products, right? And so rather than constructing the Hessian directly, we can generalize this notion to where there's a function that we pass in, and then we can just deal with this like matrix vector product routine. So that's one aspect of Liniax. And the other aspect is that it comes with much better implementations of algorithms for solving system of linear equations, which are a bit more friendly when it comes to dealing with things like JIT and autograd and whatnot. Okay, all right, so these are installed. All right, and so now what we're going to do is we're going to import our libraries, right? And so this first line imports JAX, the top level module. And so the top level module gives us access to things like how to compute gradients, as well as some other like bells and whistles regarding program control. Next, we need something to represent matrices. And so NumPy on its own is kind of like probably the reason why Python is so popular for machine learning, and that it's a library that's been around for more than a decade that is a collection of data structures for capturing arrays and tensors, as well as operating along those things. When like all these like deep learning frameworks and things started coming out, they kind of just started from the ground up, and the syntax was way too verbose and just especially when folks were just familiar with NumPy for numerics. And so JAX does this nice thing where they said, you know what, like we're not going to have a whole new numerics library for you guys to deal with. They're just going to re-implement NumPy. That's in a way that's friendly with JAX. And so now, instead of importing NumPy like we normally would, we'll say import jax.numpy. And we'll just give it an alias because I'm lazy and I don't want to type that out every single time. We'll call it JMP. Right? So now what we do is, we'll see in a minute, like we can treat tensors as we would just in NumPy, but these are sort of implementations that are friendly with how JAX can operate and push things to different architectures. What we'll also need to generate some data is just the random submodule, right? So that just allows us to sample. Also, what we're going to do, there's also a SciPy implementation, and we need the submodule from that's stats. And so that gives us like a there's already functions to get like the log probability mass function for the SOM model, which we'll get later. And then lastly, let's just import Liniax, okay? And so let's do all three of these things. All right, so that's good to go. And so kind of to kick things off, what we can do is let's just check out what autodiff can do and what that means. And so what I'll first do is just define a seed so that we can get sort of reproducible results. And I hate to take another sidetrack real quick, but randomization or pseudo randomization in JAX is a bit different from how we typically work with pseudo random numbers in our code. Usually we just say like our norm, and it just generates a bunch of numbers for us. And we can certainly pass in a seed, and it'll give like the same output, right? It'll be deterministic given the seed, and same thing in NumPy and what have you. But typically we don't need to explicitly keep around some state for our pseudo random number generator that's handled for us behind the scenes. We don't know how or why. But JAX requires us to kind of keep that state around. And it is a bit tedious, but there's good reasoning behind that. And the reasoning behind that is when you have a large collection of machines that might have slightly different architecture, if you historically pass in maybe the same seed, right, that still might output different values, right, because it might be machine or architecture specific. And so what that would break kind of some of their internal consistencies that were needed when you need this massively parallel, but in a heterogeneous environment situation. And so we have to keep this thing called a key around. It's not much work, right? We just initialize a seed, pass it into this to create this instance of a pseudo-random number generator key, and then we just keep that with us. Okay? And so here what we're going to do is define a function called sum logistic that takes one parameter x. And so x will be a vector. And so the function it calculates is really just this, right? It's the sum over indices I, f of xi, where f is just the logistic function, right? So for each entry in x, we're calling the logistic function on it, and then we're summing across all those values. But this is done in a vectorized manner, right? So you can see here that this is the logistic function, and it's done for every value in x, and then we sum across that. Okay, pretty straightforward. So we're not going to use any randomness quite yet. So we're just going to generate a couple small numbers. So just this function here will just create 3 values, 0, 1, and 2. It creates a range that's stored in an array, right? We're going to store that in something called x small, right? So this is just going to be the vector of 0, 1, and 2. Now here's where autodiff comes in. We just call jax.grad, and we pass in this function here, sum logistic. And what it spits out is a new function that's our derivative function, right? And so now what we can do is we pass in x small, and what it's going to calculate is the derivative of this function with respect to x automatically, okay? Now, before automatic differentiation was a thing, I should also say that automatic differentiation is like I think at this point, like 30 years old. It's not a new concept. In the 90s, there were already algorithms coming out, but there wasn't really a good use case for it yet. And I think, machine learning and deep learning, where it was just, no one wanted to compute those gradients by hand, right? It's just insane, where it really found a home. But before that, right, there were certainly numerical ways where if we didn't want to write out what the gradient is or how to compute the gradient, where you can just do a numerical approach, which was just finite differences, right? And it comes back to how's the gradient or how's the derivative defined, right? It's defined as a limit, as you kind of just make a small perturbation around your point between the differences, divided by that perturbation, right? And so we can actually just do that by passing in a small value, right? Just checking the differences. All right, and so here we define a function called first finite differences. And so this looks a little bit, there's a lot going on here. So let's unpack this, right? And so we just have some small number epsilon, right? And then what we do is we add a little bit to x in the direction of v, and we subtract the function where we remove a little bit of x in the direction of v divided by 2 times the epsilon. And we do that for each vector in the identity matrix, right? And so all we're doing is really just, for each entry in this, we're just moving it a little bit, okay? And then we return that. And so here, we're going to call in sum logistic, which is our function f. We call in pass in our values x, small. And so now we can compute the numerical. And so let's run this code. Okay, and so what we're going to see is we'll print the gradient that's computed by JAX, and then we'll see the gradient that's computed by the method of finite differences, and we'll just check to see if they're close enough. Okay, up to some tolerance. Okay, epsilon is 10 to the negative 3, so I'll set the absolute tolerance to be around that. Okay, we run it, and boom. Right, and so we get the autodiff gradient. We get these values here. The numerical approach, we get these values here, and they're pretty close. Right? So it looks like JAX is doing the right thing. You know, how it does it, I don't know. But it does it, right? I mean, you know, I have some sense of doing it, no, but really what it's doing is JAX will first build the call graph for this function, right? It's essentially traversing it, right? And so it enters this function, it sees that sum is being called on some quantity in here, right? And so it knows that it needs to take the derivative of this sum with respect to the inner part. Then it evaluates the inner part, and it sees 1 divided by something, and says, okay, well, I need to take the derivative of that with respect to that something, right? And then the derivative of that something is 1 plus this, and so you can see what's happening here. It's just the chain rule, right? And so if we're doing forward mode automatic differentiation, right, it's essentially just the chain rule, right? Until it gets to something like this, right, where the chain rule kind of, you can take maybe one more step, but it kind of, there's nothing just inherent out that. And so it just has a definition, right? What does it mean to take the derivative of this function? And so somewhere behind the scenes, they've defined that, right? So taking the derivative of this function with respect to its arguments is just its arguments times that same function, right? That's just the property of the exponential, right? And so it just builds up that call graph, and the forward mode can do two things at once. It can walk through when you call it and spit out the value of that function and the derivative at the same time, right? With essentially not just a constant amount of overhead. Okay, and we can actually check that out. So we can add that here, right? And what I can say is JAX, value, and grad, some logistic, right? And we'll call this like, what did we call it earlier? Derivative function. And so now we'll say like VD function. So it's going to give us both. Or maybe, yeah, I mean, yeah. Right, and so we can say print f and say like, you know, the value is equal to, oh, we got to call it first. So value dx vd fn x small. We'll use this, and dx is equal to dx. Oh, I should say, these strings in Python are called f strings. And what it is it lets us combine a string literal and expressions that can get evaluated for us. And so all we do is we specify the letter f, the constant f, before the string. And anything in between braces in that string has to be a valid Python expression, right? It doesn't have to be just a variable. It's just any general notion of an expression that will be evaluated. And so it just provides like a concise syntax for us to kind of mix and match when we want to have expressions evaluated into a string. So let's rerun this code and see, did I do that correctly? Okay. All right. And so here we get the value, right? So if we actually evaluate some logistic, right, it has to spit out a single number, right? Because it's going to be a scalar function, as well as the gradient. Okay, and we see that we get the same gradient as we got before. All right. And what's interesting is actually behind the scenes, when we call grad, what it's doing is still calling this and then just discarding this value, right? And so if you ever need to evaluate a function and calculate its derivative, it makes sense to just call this, right? It saves you an additional pass over your function. Okay. Are there any questions up to this point? Because I know I've been talking a lot and haven't done that much code just yet.
Yes, a quick question.
Uh-huh.
So you have what is value? Because there's only one value but three derivatives.
That's it. So the function is a sum over those. And so you can think this is provides the value for each So this is the legit. So it's this, right? So this is the function, right? So if f is a logistic function for each value in that vector, right? Right there is a logistic evaluation, and then we add up all of those, right? And so the gradient should be the same dimension as the parameters of this function. And so the output is just, a scalar, but the gradient of that function is going to be a vector of the same length of the size of the parameters. Does that make sense?
Yes, thank you.
Yep. Okay, cool. All right.
So in your example then, Nick, you're computing you're computing the derivative at the 3 places where you input the x small values.
Yeah, exactly. And maybe it'll help. I can also just say, like, what is x small? Print, maybe not there. Print f x is equal to x small. There we go. So we can explicitly see it, right? So this is 0, 1, and 2. So it's a very small instance, right? But just for illustrative purposes.
Yeah.
Right. And so, maybe x is a poor, we can think of this as like, like if this was like our GLM, right? Maybe this is like the eta part that's like the linear predictor or something. Or that, this was some single value.
Yeah. Okay, thanks.
Mm-hmm. Okay, great. All right, so that's kind of just the basics of just what grad can do. This is just a small fraction of what it can do when it comes to automatic differentiation. This is doing forward mode for us automatically. Depending on the function you may have, you might want to consider a backward mode, right? So backward mode isn't going to be necessarily a chain rule evaluation. To be honest, I can't recall exactly how it works. It has something to do with some like vector Jacobian products. But I for most of the time, we don't have to worry too much about it unless we start doing some deep learning stuff where, there's some dimensionality things where it can be a bit more efficient. But, I do recommend folks kind of dive into precisely what the difference is, like the web page to see, at a high level, what the differences are and when it might be useful to use one over the other. But for the most part, we can just kind of, again, not worry and just call this guy. Now, all right, so now we've seen like what autodiff can do for us, right? Like we don't have to go through necessarily the laborious work of deriving the derivatives, or we'll see maybe Hessians for our work. We can just say, hey, Jax, take it away. But let's also take a look at what the JIT can do, as well as this function VMAP. So this is another thing that's really helped popularize JAX, and I'll describe it in a second. But again, JIT, just as a reminder, JIT enables us to have machine-level code produced on the fly, right? So we pay a constant penalty up front because it has to traverse the call graph, convert that to XLA, compile that XLA down to machine code for whatever architecture we're targeting. Let's see, okay, so we don't apply VMAP, but what VMAP is, and we'll see examples in a second, is it's a function that lets us pass in a function where we want to extend the dimensionality in some way, right? So let's say that we have some function that, maybe takes in a vector and spits out a scalar, but we want to generalize that to maybe a function that is like batched in some way, right? Where like we have a batch of vectors and we want to output a value for each of those separately, right? So we go from maybe inputting a vector and outputting a scalar to inputting, some notion of a matrix and outputting a vector. But maybe we don't know how to do that, right? We don't know how to do that for our function. VMAP will do that automatically, right? We just specify what parameters need to have their axes extended, right? And axes just specifies what dimension. And how is the output going to be extended and along what axis? All right, and so if that isn't clear, hopefully the example will help clarify. So what we're going to do is just generate some data. And so just remember earlier, I mentioned the thing about the key. We have to keep state around. We have to change the state every time we generate something random. And so in order to do that, there's a split function. And so you give it the key you currently have, you say how many times you want to split it. And for each random call, we'll use the other splits, and we'll keep this thing around for downstream splitting. So this is just a design, what's the word in software engineering, was like a design principle or something, where this is just a common way to call this to start doing randomization. And so here what we're going to do is create a variable that's essentially a matrix. And so we give it the key for our randomness call, and I just called it M key to denote matrix. And it's going to have dimensions 150 by 100. All right. And then we're going to create something called a batched X. And so this is a batch of vectors, right? And that's going to have dimension 10 by 100. And you might say, Nick, this is weird. Why is it a batched vector? That's just a matrix. You're right. It is. You got me. But, right, just for illustrative purposes, let's pretend that we have batches of who knows what tensor shape, right? But this is just kind of the simplest example. And so now we're going to have a function called apply matrix. And so we give it a vector v, and it's closing over this matrix, right? So it's we see this is defined up here, but we note that it's closing over it down here. And all it's doing is just the dot product, right? So this matrix is just a fancy, annoying way for us to call the dot product between v and this matrix. Okay. And so let's say we wanted to do that for each vector in this batched X in like a naive way, right? We're just starting to learning to program, and we're starting to get dangerous, right? But we don't understand yet. And so we'll have this thing called a naively batched apply matrix, where we give in v batched. And so here what we have is this, in Python, this is called a list comprehension. And what it means is it allows us to construct a list like using this concise syntax. And so you can see this thing in here. It says for v and v batched, right? So this is going to pull each vector, each column vector out of this, for each row. So each row vector out of this batched X, right? So we should have 10 batches, each with shape 100. Okay. And then for each of those vectors, it's going to call apply matrix, right? And that's just going to do the dot product between that vector with this matrix. And so when this is called, what we should have is essentially a list of the results of this call. And then this function JNP stack is just going to take that list and just smash them all together to get a single matrix. Okay. And so now what we're going to do is there's this magic word. So this isn't a Python keyword. This is a keyword for notebooks, where it allows us to time how long this operation will take. There's one other sort of sharp point to note is that JAX is like an eager evaluation, and that it will call a function and keep on going even if the result hasn't been returned yet. But it'll stop when we need the value, right? And so like if this returned something and we weren't using its value anywhere, the code would just keep on going past it while it's executing in the background or whatever. So if we want to get accurate timing, right, we need to just add this thing called block until ready, right? And so we typically won't need to use this in any code we write, but if we want to get just accurate timing, we just need to tell JAX to say, hey, don't like lazily evaluate this, just stop until it's actually done. Okay, and so let's run this. All right, and so you can see here, it's like defining this function, it's calling this a bunch of times, bouncing back and forth. All right, okay, and so it ran what, like 1,000 loops? Or no, so, yeah, 7 runs, 1,000 loops each, right? And so the average was 900, microseconds, right? With some plus or minus standard deviation, okay? And so what we've, again, all we really have done here is just a very inefficient matrix product. But under the notion of where we have a batch, right? And we're looping over this and stacking things, okay? So it's kind of slow. All right, so now what we can do is let's see what JIT can give us, right? So now what we're gonna do is say batched apply matrix. And so now we're smart. And we realize, oh, look, we're just doing matrix multiplication. There's no reason to do this batching and apply things and stack it. So let's just do the matrix multiplication like we want. And so here we can use the dot function. And so this will spit out the equivalent result of all of this, but without the loop and the lists and everything. But also, we're going to add this, we're going to now see the benefit that we get from JIT. Okay, and so this syntax here is like what's called a decorator. And so it allows us to decorate a function. And so really this is syntactic sugar for passing this function into this function and spitting out a new function, right? But that's kind of very verbose if we manually did all that work. So Python just has this nice syntax to say, you know what, like I'm just going to put this @ symbol before this function and give it the name of this function. And this is really just going to modify for us this function. And so anytime we call this directly, it'll be the version that's already been applied that has like JIT applied to it. Okay, and so now we're doing the manual batch also with JIT. And so let's run this and see what benefit we get. Okay, so it's running. And so now we just see that we got like, what is it, like 100-fold speed up. We went from 900 microseconds down to 9 by using this just-in-time compiled. And so, you know, that's not just from just-in-time compiled because we're doing two optimizations here. One, we recognize that the batch is a single matrix-matrix product in addition to this. So what we can do is we can also take a step back and say, let's get rid of this decorator and like explicitly make a function. Okay, and so manually batched, we'll say JIT. I'll just copy and paste this, and then we'll say this and call the new function. All right, so if we wanted to manually call the just-in-time compiler on a function, we just pass it into this function here, and it spits out the new function. Okay, and so here what we're doing is we're calling this one up here, and down here we're just recalling the same function, but after it's been compiled. Okay, and so let's see if there's, you know, an added benefit of going from the dot product to the just-in-time dot product. All right, so we see that we went from 900 microseconds down to 60 just by recognizing that we should just be doing a matrix product, right? So that's our algorithmic improvement, let's say. And the improvement we get for free from JIT, right, is another 6-fold. All right, so we're down to 10 microseconds, which kind of matches, you know, there's some stochasticity here earlier. I think when we ran it was around 9, right? Okay.
Nick, a quick tangential question. Where's the 7 coming from? Why is it doing 7 runs? Is that just how many times it chooses to do it to estimate?
Yeah, I think so. There's probably some parameter in here that you could specify with a flag or something.
Okay.
That's all. I don't know. I know there's options for this, but I never learned it. So, okay, cool. Right, so we got the speed up for free, right? The first one was us having to use our brains for a second, and the second one was not, just knowing that this thing exists and we pass it in. Okay. So now, you know, let's see what VMAP can do for us, right? And so what we're going to do is go to the original function all the way up here, apply matrix, which is just this matrix vector product, right? All that's doing for us is matrix vector. Whoops. And so now what we're going to do is you see that we're calling VMAP and we give it this matrix. Okay. And so in this case, there's some default parameters that work out for us, right? Because there's a single argument and there's a single output, right? And so if we don't specify anything else, it's going to know that we just want, by default, it thinks that the batch axis is always on the left, right? And that if we look at when we made this, right, this is our batch axis, right? And so if we pass in a vector that just had length 100, right, after VMapping that function, it knows that there's a new axis here, or a new dimension to the left, right, that corresponds to the batch. Okay. All right, and so we call VMAP and we pass in our batched vectors, or our matrix, right? But we also get called JIT on that. And let's see how we do. Right, so now we're going to call VMAP on this one, on this function here, and block until ready. Let's see what our average runtime looks like. Okay, So 15 microseconds, right? So it's a little bit slower than us making our algorithmic improvement and then calling JIT. Well, not so bad, right? And then here, I mean, this was a very simple function, right? It was like obvious how to make this algorithmic improvement. We're like, oh, we're just doing matrix multiplication. But for some complex functions, right, that might be 100 lines long, that have submodules that get called or whatever, right, it might not be immediately clear how to vectorize it, right, without doing a lot of work, right, without like stepping through and kind of keeping track of the dimensions as we go, right? And so sometimes we might be willing to make the trade-off where say, all right, you know what, like, I'm not going to go through the bug riddle process of trying to extend my function to consider another dimension, right? I'm happy with a small hit and having it do it for me, right? And so this takes me back to like to Dijkstra, who is the scientist I recommended, who's like a huge character. If for folks who are familiar with him, he's just extremely opinionated man when it came to programming. Wrote numerous essays, which sort of captivated the field of computer science back in like the 60s. I think one of his most famous is like go-to statement considered harmful, right? And he was very against the notion of go-to because it could just like you had arbitrary control flow. And he like just thought it was like the worst thing to be introduced to programming back in like the 60s or something. Go-to has its place, but I think at the time when the way folks were using it, anyways. So it was very opinionated. So I thought it was funny that, debugging is the process of removing bugs, and programming by definition is the process of like putting them in. And so if we want to avoid that process of putting them in, right, this is where VMAP is very helpful. Okay. And here we had, this was like a very simple function, right? It was just, this apply matrix just was like one argument. You can imagine that we have multiple arguments and maybe even multiple outputs, right? And then VMAP, provided we just specify how we want to extend what, or extend nothing, right? In some cases, for some parameters, will do it for us. Okay, it might not do everything we need, but it can get us pretty far. And it's very, very helpful and cool. So are there any questions about just-in-time compilation or VMAP?
You have a question in the chat window?
Oh, I see. Does the batch operation come with a cost of memory usage, like a trade-off? Well, so that's a good question, right? You can imagine that if you want to batch and do everything in parallel, right, then there will be inherently a memory cost because you're just doing things in parallel. Versus, if something was iterative and you wanted to add them up or something, right, then that would have reduced memory. But if the goal is to just that those things would need to be computed anyways across those batches and all would need to be stored, it shouldn't introduce a large overhead. I imagine maybe there's some constant amount of overhead just from how the function works, but I don't think it would be considerable compared to hard coding it ourselves to consider an additional dimension. So the other thing too, just I want to mention or touch, we're almost out of time, but just-in-time compilation comes with a lot of caveats. Right now, these are very simple functions that we wrote. We can certainly call just-in-time compilation to a much more complex function that has control flow, loops, things like that. Gradient will work over those just fine, but if we want to do compilation, right, then there might be some gotchas that have to be considered. I don't think we have time to go over those in detail for today, but for folks who are very interested in this framework, I just encourage you to go to just the website, or if you just go to the JAX website, I think there's something called the sharp bits, and they'll show you where things kind of break down and how to work around that, right? So it doesn't mean that you can't use JIT, but rather than just having an if statement, you might need to have a function that they have that's like a functionized if statement or a functionized for loop or something like that. Okay, cool. So I don't know if we're gonna be able to get through all of this, but what I wanted to do was just illustrate a bit more complex example with just Poisson regression. I don't want to get into the whole of it like a GLM, so we'll just focus solely on Poissons, and then we don't have to worry about links and all that, because it's just I'll get confused. So it's just easier to do this. So imagine what we have is a bunch of paired data, right? We have a bunch of Ys and some corresponding vector for each y. And we think that y given x is distributed Poisson with some lambda parameter, where that lambda parameter is really just the exponentiation of this linear product, right? So we have a bunch of betas, and we just, for the given x that's known, we just take the inner product, we throw the x around that, and that defines the mean or the lambda parameter for this Poisson for this individual, okay? And so it's called, Poisson regression because what we want to learn are these betas, right? And so what's our loss function, or what's our function we want to maximize alternatively? Well, it's just going to be the log likelihood, right? Oop, this is, let me edit this. Hold on, y given, there we go. That's better. Okay, right, so this is our loss, or well, I should say our log likelihood that we want to maximize. It's just going to be, we assume these are all independent, right, given x, then it's just going to be the sum of the log probability mass function from Poisson for each of the y's, given this. Ooh, darn it, I'm making a lot of mistakes. Let's say x. There we go. That's better. Okay. So I went ahead and did some math for us already. And so what we can do is compare, if we wanted to do the work, right, of computing the gradient of this. The gradient of this, if we stack all these x's together and make a big matrix, and stack all the y's together to make a vector, right? The gradient of this is going to be x transpose the difference between y and its predicted mean, right? And then the second order information is just going to be this weighted gram matrix, right? And so here it's just, these are our variables x transpose this diagonal matrix lambda x, right? And so this is really just the predicted weights, so the predicted means for each observation just along a diagonal, right? So we're just weighting each observation here by predicted mean. And the reason for that is that's the Poisson has the same variance and mean relationship. And so this is really supposed to be like the variance. And so one classical way to fit this is just iterative reweighted least squares, which is like repeatedly solving like a weighted least squares problem, and so we can think if we were just doing like Newton's method over this, we want the new value at time t+1 is equal to the old value, where we have the inverse of this Hessian, right, times the gradient, right? And so this is the system of equations we can solve. But we can do a bit more work and push things around and do a single solve just directly. And so what we have here is if we weight x by these observations and we remove those from y and add the last round's predicted value -1, then this is what we can call z. And then here, this is what we can call z. And we see this is like the system of equations we want to solve, right? Like the unknown here is the new beta time t+1. And so let's look at how we can write that out in code if we want to kind of manually do this ourselves, right? And so what I've gone ahead and defined is this log likelihood if we are given eta. And so eta is just this, is what we would consider this. And we throw that through the exponentiation to get the means for everybody. I can't, as much as I want to call this result lambda, we cannot, because lambda is a keyword in Python, right? And so the best I can do is mean lambda, okay? So just bear with me, right? And so now what we do is we call stats.Poisson. So this is from our SciPy module that we pulled in. We say we want to look at the Poisson, we want its log probability mass function, we give in the y's, given all the lambdas, and we just add those up. Okay, so that's our if we want to evaluate things, okay? And then separately, if we wanted to pass in just beta itself, right, then internally we can compute these things. This looks a little bit different than what we've seen. I'll explain that in a second. All right, and so if we are doing our iterative reweighted least squares fit, right, all we do is we compute our diagonals, we compute z, which again is just y divided by d plus eta -1. Remember, it's this thing. So this is why I use Lineax, why I like it. And so I construct something called x star, which is the weighted set of observations. So x is weighted by the square root of their lambdas. Okay, and so this actually isn't computing anything. This is just using the Lineax operator framework. This just constructs a new operator, right? So nothing really is computed here yet. And so then I call linear solve using lineax. I say, hey, here's x star and here's z, right? But that's not, we're not solving for x star and z. We're supposed to be solving for like x star transpose x star, right? What gives? Well, I tell it there's this nice solver that says, hey, I want to solve the normal equations for this model, right? And so the normal this is the normal equation, right? It's a regression model, right? We need to square this matrix and then do the same, consider the same thing over here. And we want to solve that using conjugate gradient, right? And that's an iterative approach. Okay, and so we just call this, we give it this operator, give it z, behind the scenes, it'll construct everything it needs, and we can pull the solution. All right, and so now what we have here is a Poisson regression using this. So we pass in y, we pass in x, maybe just give it some maximum number of iterations, compute some initial eta just from some guess. We'll take our NumPy matrix, wrap it as a linear operator, and then we'll pass it into our fit function, giving our start eta, which is going to spit out our updated version of beta. We're going to update our eta. We're going to recompute the log likelihood, and then we're going to see how things go. And then when delta is not so different, right, the change in the log likelihood between iterations, we just short circuit and return the current estimate of beta. Okay. So right now we're not leveraging any autodiff or anything like that. But what we can do is at the very least, Jack's JIT around this. And so this should be faster, let's say. And so now let's generate some data. Okay, so first let me evaluate this so these things can exist. All right. And so now let's say we have 100 individuals, man, I'm almost out of time. P observations. I'm going to split my key, have a y, something to generate y's, something to generate x's, something to generate betas. We generate x, just say it's shape n by p, just some, every entry's IID. We generate betas, IID, that's shape p, okay? Here we can use this notation because this is still like a JAX matrix. We're just doing a matrix vector product here, throwing that in the exponentiation to get our mean lambda. And then now we sample from the Poisson around that for each person to get our y, right? So we just did a little simulation here just to create some fake data. And so now let's see if this actually runs, okay? I haven't run this, so this is like a moment of truth. Okay, so it looks like there's a bug, unsurprisingly on my part, because we have some flip-flop. So let's see, are we even improving? No, so something is going wrong, dramatically wrong. Let's see, where could that problem be? What am I doing wrong? All right, square root, x star, z, this d, yes, x, this, that all looks fine. This should be fine, right? Because eta gets exponentiated, that's fine. So we fit, update the new one, compute eta. Let me make sure I exponentiate the eta, log PMF, yeah, that looks fine to me. So what is going on? Why doesn't it like it? Well, I will find out, considering that we're out of time, and fix it. That's what I get for not being so diligent. But I guarantee you this is not a problem with JAX. This is a problem between the user and the keyboard. But you know what I wanted to show is like how it's not a lot of work to get things going, right? And this is us still doing the derivatives on our own, right? We could easily do this. Right, and just say like, you know, auto. Right, and now what we'd like to do is say we want the value grad fn jax value and grad of this function. So actually let's do this up here because we'll create that once outside of the loop, and we can call jax.jit on that. Right, and so now what we can do is say new log likelihood grad is equal to value grad fn. And then what we would need to pass in, this would be a bit different. We need to initialize beta. So we'll say beta is zeros. Let's say np x shape. There we go. Hold on. I don't think we're gonna have time to really look at this. And then beta grad. We'll say beta is equal to beta, I don't know, plus 0.0 times grad. This is our gradient step. But right, this is like how we could easily just do gradient descent if we wanted to. Right, so we're updating our beta, our gradient ascent. Right, we get our function, we get the new log likelihood, and we update. Update beta using the gradient computed here. So what I can do is I will take a separate pass over this that also explicitly computes the Hessian using autodiff, and that way we'll have a fair comparison between the two second order methods of these approaches. Right, one where we explicitly did all the work with iterative reweighted least squares, and one where we just have JAX compute the gradient and the Hessian, and we still do a Newton step, but using all these things for us. I know that was a lot of information, and it was a lot of me kind of going back and forth at like high level things and like maybe very too terse of examples. So I'll try to also add a bunch of notes that might and links within this document that can help folks further explore this stuff.
Nick, apologies for another tangential question, but does Colab offer a debugger of any sort? And if not,
yes,
how much
I think, let's see what happens. Like, can I add like a breakpoint? If not, what we could do is, I mean, so Python has one where you could say like, import PDB. That's the Python debugger, and we could say like set trace. And so like right here, basically a breakpoint would get hit. And then like with the debugger will open up, and so we could add additional breakpoints and things like that. And so that's what I tend to do like on my own code. There might be a way just to, I know like in IDE, you can usually just like double click, right? And it'll add a breakpoint. There might be a way to do that, but I'm not familiar off the top of my head. Well, I hope that was at least mildly informative, and at least might pique some folks' interest in exploring this a bit further. If anyone ever has any questions regarding this at any point in their time regarding research, I'm always game to chat because I really like this framework a lot. And so I'm more than happy to help folks with any of this. Cool. Thanks, everyone. Oh, hey, Lou.
Yeah, it looks so exciting. I'm curious about the speed between like the JAX and the Julia. Do you think the JAX can be faster than Julia?
I don't think I can see in instances where it's probably very similar, right?
Similar?
I still think there are, I know that Julia already is like a statically typed compiled language, and so it's going to be hard. There's the added overhead of the just-in-time compilation, right? And so even though we get to the metal at some point, there's still that constant, runtime compilation that we have to hit. Whereas Julia, you compile once and you're good to go, right? But I do think once things are going, right, that speed can be very comparable, right? And JAX is a Google-backed product, so it's not going anywhere anytime soon, right? And if anything, it's just going to get more and more attention. And so I really like Julia a lot, but I do know that there's a trade-off in terms of how much effort is being placed into robustifying certain aspects, numerical aspects of Julia, whereas if Google's throwing their weight right behind JAX as a machine learning framework, then like it's going to get the treatment it needs. So
I see.
cool.
Yeah.
But that's a good question.
Yeah. Actually, leave a quick note in the chat. I think that maybe in the line of the in the line you use the conjugate gradient, I think you forgot to rescale the z. Maybe that's where the bug is. Yeah.
Oh, here? Oh, well,
Yeah.
here this by default, because here this is the
Yeah,
right.
but if you check your equation, like Z should
Ah,
be rescaled. Like screw up, you can check the equation. Like
here?
yeah, the lambda. Like you
Oh,
actually
you're right. You're right. No, you're right. It is right. Ah, see, that's why.
That's the best debugger of all, right? Your audience
I
is supposed
know,
to be
right?
technical.
Let's see. Did that fix it? Ah, good catch. All right, there we go. Looks like it converged pretty quick, right? It's having trouble with that last little bit, but nice. All right, so what are the true betas? 1.64, 1.43. Yeah, pretty close. So, all right. Well, thank you. That was the perfect way to end that. I appreciate it. I owe you like lunch or a beer or something.
No, I'm very excited to know the autodiff. Actually, I use Stan when I like
Oh yeah.
from the very beginning. I use Stan to do autodiff, and I'm very excited to know that Jack can do something like very similar and much easier. Like
Yeah, I mean, Stan is phenomenal, right? Stan, I think, paved the way for a lot of the autodiff stuff. And so, I know in a lot of ways things have kind of moved beyond it, but like, Stan really, really demonstrated the utility of autodiff in statistics and numerical computing. So yeah,
cool.
yeah, super cool. Thanks everyone. Again, I'm happy to chat, and I'll update this document with more information.